Okay, welcome back, everyone. So we're very happy to have Adrian Vladu from CNRS.
Cool. So yeah, thanks everyone for being here. So this is a very amazing audience. It's very humbling to be here in front of everyone. So I'm gonna okay. So this talk is about some work that I did with Lucas Pesenti when he was a master's student at IRIF, and now he's a PhD student in Italy. And we worked together on discrepancy. And yeah, now I'm going to get to tell you a bit about the work that we did at that point. So first of all, let me just so normally I would talk about efficient algorithms. So this is not the typical talk that I give. So let's just see how this is going to go. So today's topic is a bit different from what I usually do. So it's combinatorial discrepancy. So this is a field of combinatorics that has seen a lot of progress coming from the theoretical computer science community. And there are many very exciting results. Within the past years, we've seen many exciting results that are kind of like made progress on this field, and they're also algorithmically relevant. So let me start by introducing the classical problem discrepancy, which is Spencer's problem. So what is this problem? So imagine that I give you a ground set of n elements and think of them as these black points, and a family P of m subsets defined over this ground set of elements, and think of those subsets as these ovals. My goal is to color each of these elements in my ground set with one of two colors, either red or blue, such that each set has a balanced coloring. So what does this mean? So imagine that this is my coloring. Now, so basically what I'm trying to do is that I want to minimize the maximum imbalance, in the sense that I want each of these sets to have roughly the same number of red elements as blue elements. Okay, very basic problem. Okay, now let me try to introduce a bunch of definitions. So basically, given a coloring X and given a set S, I'm just going to say that the discrepancy of that set with respect to that coloring is the absolute value of the difference between the number of blue elements and the number of red elements, right? So this set has discrepancy 0 because it's perfectly balanced. So this one has discrepancy 2, this one has discrepancy 2, and this has discrepancy 0. And the discrepancy of the coloring with respect to the set system is just going to be the maximum imbalance that this coloring achieves over all of these sets in the system. Make sense so far? So basically, I'm just going to measure the maximum imbalance among all of those sets in my family. So the question that we want to answer is, how small can we make this discrepancy? Well, okay, do you have any guesses? Well, let me just start by slightly rephrasing the problem to make it even more accessible. Let me just encode each color with a number that's going to be either +1 or -1. So basically, what this thing says is that I can just measure. So basically, if I just assign a +1 or -1 to each element in my ground set, I can just measure the discrepancy of a subset as the absolute value of the sum of these numbers associated to the elements in my set. Which one?
Move the whiteboard to the right.
Good. Okay. All right. So, okay. So how small can I make this thing? Well, you probably already know that the textbook approach tells us that the first thing we should ever try is to just throw a random coloring at our elements. So basically, if I hit the elements from my ground set with some random ±1 coloring, I can just start writing basic tail bounds. Because, basically, if I just measure the discrepancy for a fixed subset, that's just going to be a sum of Rademacher random variables. And of course, for these, I have standard tail bounds. So basically, it tells me that if I just look at a fixed subset, the probability that the absolute value of the sum of these numbers, which are random ±1 numbers, is going to deviate a lot from the mean. The probability that it's going to be larger than 100 times square root n log m is going to be pretty small. Right? So basically, so remember that m is the number of sets I have, and n is the size of my ground set. So, basically, if I just basically, if I just try to measure, if I just try to write the stale bound, it says that, there's a very small chance that any of that, fix that, that the imbalance here deviates by more than this much. And of course, now I can just union bound over all of the sets in my system, right? So the things that I have m systems, I have m sets. The probability of a bad event for each of them is bounded by 1/2m. So, basically this just tells me that, with probability at least half, the discrepancy is going to be bounded by order root n log m. So everything standard so far. I haven't done anything too fancy. But now the interesting question appears. Is this really the best thing that I can do? Is it possible? Basically here, I kind of ignored correlations between all those subsets in my family, right? I just considered them, I just looked at each of them separately. I just threw a union bound at them, and this is what I got. Well, it turns out that, this bound of root n log m is not tight. In fact, Spencer managed to prove in 85 that something actually much better can be achieved, right? So he managed to prove that there exists a coloring that achieves a discrepancy of order root n log m over n. So the case we have to focus on is the one where m is about the same as n, when m is order n for square matrices. In that case, his discrepancy is order root n. And in fact, he managed to prove that the discrepancy is at most 6 times root n. So that gave the title of his paper, 6 standard deviations suffice. So this is kind of puzzling, right? Because, union, concentration bound plus union bound is kind of a standard technique, but he somehow managed to beat this thing. So, okay. So, like the original, I wanted to mention first that the original result that Spencer gave was existential, but then following that, there was a very long line of works that came up with that produced algorithmic results. So notably, Bansal first gave some algorithmic construction, and I'm pretty sure that a large number of many people in the audience had worked on some of these results. Now, okay, I wanted to mention why do we even care about, we have all of these previous algorithmic results. Why do we even care about, coming up with yet another algorithm for discrepancy? Well, the point is that many of these results use pretty different techniques. And, while trying to achieve them, they kind of like manage to uncover a bunch of mathematical techniques that we can actually use to prove the existence of rare mathematical objects, which, which are hard to identify by just throwing vanilla tools like union bound. So, and while proving these things, a whole bunch of interesting connections were made. So, it should be. This effort of studying discrepancy problems should be worthy, even if we manage to rederive some of the old results along the way. Okay. So now, to give, yep.
Is this type? Is this meant to be typed log m over n?
Oh yeah, so this is actually tight. So it's actually quite easy to construct. It's actually quite easy to construct tight instances. So for example, the one where m is order n is exactly tight. You can just give a scaled Hadamard matrix, and you can do something similar to prove it for general m. Yeah, thanks.
Actually, I think for random sets it's type too.
Yeah, that too. All right. Now, to talk a bit more about discrepancy and why we care about it. So let me first give you a slightly cleaner linear algebraic view of the problem. So we can do this thing by encoding our set system into a matrix that's going to be m by n. So each row of the matrix is going to correspond to a set. Each column is going to correspond to an element, and basically I'm just basically each row is going to be the characteristic vector of of a set from my system, right? So basically for the ith set in my system Si on the ith row of the matrix, I'm gonna put a 1 on column J if element J belongs to the set and a 0 otherwise. So then I can just like see what happens when I hit this matrix with a vector that encodes my coloring, right? Basically, I just go, I just like compute A times X, and I'm gonna get some. I'm gonna get some as an output a vector where the elements encode, the absolute value of these elements encode the discrepancies that this coloring gives me for each of these sets. Right, so basically, using this linear algebraic view, we can see that the discrepancy of a coloring X is just going to be the infinity norm of AX. Good. Now, this is not the only problem that people care about. There are a bunch of other very interesting regimes. Notably, the first one we care about is the Beck-Fiala problem, which is quite interesting. So basically, it's a very particular instance where each column has bounded sparsity. It has at most S non-zeros. And in fact, for such instances, people managed to achieve much better discrepancy bounds. They managed to prove that, for such instances, one can achieve a discrepancy of order S. So note that this is independent of n, or square root S log n. So, like basically this one is independent of n, whereas independent of the number of columns, whereas this one has a better dependence on S, but depends logarithmically on the number of columns of my matrix. And of course, it's conjectured that one can actually achieve a discrepancy bound of order square root S, but in fact, not even S 2.99 is known. So if you manage to prove anything like that, that'd be a pretty major breakthrough. And okay, so this is the Beck-Fiala problem, and there's actually a further extension, which is even more interesting, which is the Komlos problem. So here, my matrix is just going to be a real matrix, and my columns are going to be real vectors whose L2 norm is bounded by 1. And it's actually, so basically in this case, what we're trying to do is that essentially we're just like trying to come up with we're trying to find signs for all of these column vectors that are bounded in L2 norm by 1, such that their sign sum has small L infinity norm. And in fact, using a whole bunch of pretty clever convex geometry, Banaszczyk originally managed to prove that one can achieve a discrepancy of order square root log n. And of course, it's conjectured that one can achieve a discrepancy of order 1. And note that this problem is actually much stronger than Beck-Fiala because it implies Beck-Fiala, right? If you give me an instance of Beck-Fiala, I can just scale down my input by a factor of 1 over root S. I get a Komlos instance. Whatever discrepancy I get for the Komlos problem translates into a discrepancy bound for Beck-Fiala scaled by a factor of root S, right? So like root log n discrepancy for Komlos implies root S log n for Beck-Fiala already. And if anyone manages to prove this thing, we also get what we're hoping to get over here. So now the thing is that, like this is like a pretty exciting problem. Like the way people manage to prove things like these, Banaszczyk used a bunch of very ingenious convex geometry. And, this is also kind of like related to the suprema of Rademacher processes, which is something that Telegrant worked on very hard. So, it's actually quite interesting. There are many interesting connections to draw from studying these problems. Now, okay, so we can move on and talk about this thing a bit later. I wanted to just like move on a bit and just go to the objective of this talk. So the objective of this talk will be twofolded. So first, I want to present you a very simple algorithm that basically that gives yet another constructive method for proving Spencer's theorem. And it's kind of nice because it's based on Newton's method, which is some optimization method that optimizers like to use a lot. It's very common. In fact, using this method, we can actually improve the constant in Spencer's bound. So we can prove that 3.67 standard deviations suffice. So this is nice, but like even further, we can kind of like use these techniques together with some idea put forth by Potokuchi, where he was trying to actually prove that the Komlos conjecture is true for pseudorandom matrices. So basically, we managed to prove that for the right notion of pseudorandomness, one can actually prove a discrepancy of order 1 for Komlos instances. And the way this thing is done, is basically we can like build on some idea, that Potokuchi used to prove, the corresponding version for the case of the Beck-Fiala problem. So I'm gonna start by presenting you this algorithm, and what's gonna be nice about it is that it's also going to highlight a bunch of interesting obstacles that appear whenever we try to prove these more interesting conjectures. Do you have any? Yeah.
So it seems. Is it true that for random instances, it was known that Komlos conjecture holds with a constant?
So I'm not sure. I don't think that anyone knew how to prove this thing before.
I see. Right. Okay, so basically your proof is the first that establishes this for random as well.
Yeah,
okay,
so I mean, you can do it for all sorts of interesting pseudo-random instances, So like specifically, there's this example that I find very difficult, which is, just rotation matrices. If you manage to prove anything about that in the worst case, you're probably gonna make a lot of progress towards towards this conjecture in general. We at least managed to prove it for random rotations. Okay. All right. So let me just move to describing the algorithm we use for proving Spencer. So basically, the algorithm follows the blueprint of other similar algorithms, such as the one of Lovat-Meka and Plevy-Ramadas Rotvos. Which is based on kind of like constructing a fractional coloring. Basically, constructing a fractional coloring that we kind of keep evolving by moving a particle through the unit hypercube until we eventually hit a corner, which is going to give our solution. So to make it easier to understand the algorithm and the analysis, let me just slightly simplify the objective. So instead of looking at the L infinity norm of the matrix AX, let me just try to look at the maximum value of maximum entry in AX. And I can do this thing very easily. I can just like stack A on top of minus A and just like, try to find the coloring X for which maximum of this new matrix times X is going to be bounded. Good? All right. So again, we interpret the sought coloring, which is a ±1 vector, as a vertex of this unit hypercube. And again, to construct this coloring, we start with some point at 0, and then we iteratively move it through this hypercube until we eventually hit a corner. Now, in order to be able to do this thing, we need to enforce a bunch of invariants. One of them is that at every single step, the way I'm going to update my current point is that I'm going to update it with some direction delta that's orthogonal to my current position X. And the reason why I do this thing is that because this enforces some sort of monotonicity, because it forces the invariant that the squared L2 norm of my current point always increases, is monotonically increasing. And the other thing that I'm going to enforce is that once my point hits a face of the hypercube, I just freeze that coordinate that hits the face of the coordinate. I never change it again. So that means that in the long run, I just keep increasing the squared L2 norm of my X. Eventually it hits a face of the hypercube, so it freezes that coordinate, and it keeps doing this thing until the square L2 norm becomes N, which means that I found a corner of the hypercube, and that's going to be the coloring I return. Okay. Now, so this is what I need to enforce in order to make sure that I return a coloring. Now, the difficult thing is that as I evolve this fractional coloring, I really need to control the growth of this function, which is the max of AX. Now, this is going to be a bit annoying because the maximum function is a nasty function. It's not even continuously differentiable, and it's kind of hard to track its evolution as I change X. So what I do, instead of directly tracking it, is something that we like to do a lot, which is to just replace this maximum function with a smooth approximation, phi. And how I come up with the smooth approximation, what smooth approximation of the maximum function I use here is really going to determine the outcome, the outcome of this algorithm, the discrepancy bound I managed to prove. So basically, I'm going to do a brief interlude. So to show you how to derive such smooth approximations. And the answer comes from convex analysis, where a standard way to make a nasty function smooth is this technique called regularization. So, okay, and we're going to do this thing in 2 steps. So first, let me just write the maximum function as a linear optimization problem over the unit simplex. So basically, if I want to compute the maximum of some vector y, what I really want to do is that, I'm going to cast this thing as finding the vector p defined on the unit simplex that maximizes the inner product between y and p. Now, this is not something very clever because, because the p that I want to produce is going to be supported at a single coordinate. It's just going to hit exactly the largest coordinate in y. But what I can do is that I can just fix this thing by adding a regularization term omega, which is going to be, some nice convex function, which is basically going to penalize me whenever this p is very spiky. So it's going to encourage me to kind of more uniformly distribute the mass over this p that I use it to hit my y. Now the effect of this is going to be that it's basically going to round the corners of this function. So for example, you can just stare at this plot. This is going to be the maximum function plotted in for 2-dimensional vectors. This is going to be the regularized maximum that I obtain if I just throw some nice convex function on top of this. And actually, there are some very standard choices of regularizers that people use. One of them that's very standard is negative entropy. Basically, if I just hit this p with a negative entropy function, what I'm going to get is going to be this smooth approximation of the maximum function, which is log sum of exponentials, which is exactly what we are analyzing whenever we study the multiplicative weights update method, or whenever we try to derandomize Chernoff bounds. Now, okay, so this one shows up very naturally, and you're very familiar with it. Now, the one that we're going to be using here is going to be a bit more funky. So it's going to be this square root regularizer, which looks a bit different. It's basically just going to be determined by a sum of square roots of entries of the vector p, of this probability distribution p. Now, when I explicitly write down I explicitly write down the smooth approximation phi that I obtain by using this regularizer, I'm going to get something that looks a bit funny. It's going to be a bit interesting to parse it. So it's basically going to be, a scalar, it's going to be the result of a scalar minimization problem where the scalar here, lambda, is going to achieve a trade-off between 2 terms. On the one hand, I want this lambda to be larger than the maximum value of y. But of course, I don't want it to be too large because, because if it's too large, then, the value, then this term is going to contribute a lot. On the other hand, I have this other term, which basically penalizes me whenever lambda gets very close to any of the entries of my vector. So in some sense, this acts as some sort of barrier term, which basically says, okay, well, I want to make this thing as small as possible, right? While being at least as large as the maximum entry of y, but I don't want to make it very small. So this is going to repel me from the largest entry. Now, as weird as this may look, this is actually a nice and different. This is going to be a nice differentiable function that's going to have that has nice gradients. So that's going to have nice and Lipschitz gradients, and this is exactly what we're going to be using here. Okay. So, okay. Now, the thing is that what we managed to achieve by introducing this regularization term was that it helped us turn this maximum function into a nice function that's continuously differentiable and has nice properties. On the other hand, Well, we have to pay something in exchange because, we are modifying our function, so we introduce a bunch of error. So we need to pay up for this error up front. So this is going to, and we need to control this error. But in exchange, we get the nice differentiability properties. Now, this error is kind of important because, it really depends on the choice of regularizer we use. And we're going to get back to that in a bit. Now, let me, okay. Okay. Now let me try to go over the good things. What the good things that follow from regularization. Well, once we regularize a function, once we compute this regularized maximum, now all of a sudden it becomes differentiable and has nice properties, and we can just track how it evolves when we make a tiny update, right? Basically, if I move from y to y plus some delta, I can just measure how much my new regularized maximum will be compared to the old one by just looking at the first order term, which is going to be the inner product between the gradient, the gradient of this phi, which actually happens to be exactly the probability distribution that achieves the argmax over here. There's going to be a second order term that involves a quadratic, involves a quadratic function with the Hessian of this regularized maximum, which is just like, something that depends on my probability distribution P, and some higher order terms. Okay, so it has nice properties, it's differentiable, and everything. Now, the thing is that what's going to be very important is that once I look at the second order term, its contribution really depends on the choice of my regularizer. So for example, in the case of negative entropy, basically, I can just bound the contribution of the second order term by the inner product between my probability distribution P and the pointwise squared vector delta that I use to update my current y. Now, whenever I use the other regularizer, the square root regularizer, this thing actually becomes much more tame, because I can actually bound the second order term by something that, involves the inner product between, the pointwise squared update delta and this probability distribution to power 3/2. So, while in the worst case, when P is very spiky, there's no big difference between these two. Imagine the case when this is uniform, when this is relatively uniform. In this case, this is actually much smaller. It can be smaller by a factor of like 1/√m. So basically, what I managed to buy here by using a different regularizer is that I can actually control the growth of this regularized maximum much better. What I pay for it in exchange is the error that I introduce. While in the case of negative entropy, the error I introduce is going to be log n. In the case of this square root regularizer, it's going to be something that's going to be order root n. So this is the kind of trade-off that you achieve. But for our purposes, this is actually going to be much more useful. Okay. So I defined the smooth approximation of max that we're going to be using. So all we have left to do now is to control the speed of increase of our regularized maximum phi. Right? So basically, what we're going to try to do, whenever we move from x to x plus delta, right? Now we know exactly that the squared L2 norm of our iterate is going to increase by precisely square L2 norm of delta. What we're going to try to control will be the ratio, the ratio of the change in my regularized maximum phi versus the change in the squared L2 norm of my iterate, right? This is what I'm going to call speed. Now, using Taylor expansion, I note that this change in phi is going to be given by this linear term plus quadratic term plus higher order terms. And, I know that, this difference is just going to be exactly given by the square L2 norm of my update delta. Now, of course, when I take very small steps, this higher order term does not really matter. It's just going to go to 0. So all I need to focus on is just the first order term and the second order term. Okay. So basically what this thing tells us is that if we want to control the speed of increase of phi, what we need to control is really, this quadratic function. So, okay, so basically, how do we? So, okay, so basically, okay, now this suggests this already suggests the kind of step that we want to take. Basically, it's saying that, well, what's the best direction that what's the direction that I want to take if I want to increase the square delta norm of my iterate without increasing my phi too much? Well, basically, I can just find that direction by just like solving by just trying to minimize this quadratic over the set of iterates that are perpendicular to my current x, because I want to maintain this invariant, which tells me that I always increase my square L2 norm. So this is basically just a Newton step. Now, of course, generally, if you just so basically what I can do in continuous time, I can just solve a sequence of quadratic minimization problems of this type. Of course, I want to always move only, basically I only want to update the coordinates of x that are not frozen yet, right? So I just need to restrict the support of my delta, and I want it to be orthogonal to my current x. But now the point is that if I look at this thing, generically, if I did not have this constraint, generically I can make this quadratic negative, so that can only give me progress. Of course, I can run into trouble whenever this linear term that I use to hit delta with, A transpose times P, is perfectly aligned with X. So in that case, I really need to move orthogonal to this linear term. So I just need to move orthogonal to A transpose P. So it means that I must make this linear term equal to 0. And at that point, I really need to worry about the contribution of this higher order term. Okay, so basically, what does this? So basically, it tells me that in order to be able to control the speed, I really need to, try to understand, I really need to understand how small I can make this quadratic. Okay, now to do this thing, we're going to use a lemma, which says that whenever we have k variables available, so remember that I execute my algorithm, some algorithms get frozen, I never touch them again, and I'm just imagining that I still have k directions left to move, right? So I have frozen all but k variables. So basically, what we prove is that whenever we have k variables left available in the support, we can bound the speed of increase by order 1 over root k. And we're going to get back to this in a bit. So the proof idea is to basically show that this matrix has a small eigenvalue in the subspace that's orthogonal to x, because remember that I don't want to touch. I'm not allowed to touch that subspace. And the way I do that is basically I just bound the trace of this matrix over that subspace. And yeah, I'm gonna show you an idea. I'm gonna show you how to do this thing in a bit. Now the thing is that once I have this lemma, I can just move to the end game, because I can do this thing to measure the total increase in phi I suffer from the beginning of the algorithm all the way to the end. Well, so let's just imagine what's happening. Like originally, I have n unfrozen coordinates. So basically, I have n degrees of freedom. So using this lemma, it tells me that for as long as this happens, the speed of increase is going to be 1 over root n, which is very small. So it tells me that phi increases relatively slowly. Now, what can happen in the worst case is that I just keep increasing x until its square delta norm becomes exactly 1, and just happens that it had frozen a coordinate, right? At that point, I have n minus 1 coordinates left available, and at that point, the speed of increase of phi becomes slightly larger, becomes 1 over root n minus 1. So if I just look at this worst case behavior, it tells me that, okay, well, in the worst case, the increase in my phi is going to be at most order 1 over root n plus 1 over root n minus 1, and so on. And this is just going to be something that's about order square root n. So that tells me that, from the beginning to the end of the algorithm, my smooth approximation to my maximum function has increased by about order root n. But remember now that, like this phi at 0 is not 0, right? I must pay something in exchange for getting this nice smooth approximation of the maximum function. Remember that my function, basically at 0, the value of phi of 0 is going to be the maximizer of this linear term, which is going to be 0 minus omega of p over p's on the unit simplex. And basically, this just gets maximized when p is uniform and charges me exactly 2 times square root n. So combining these two facts, the bound on phi at initialization plus the bound on the total increase in phi over the course of my algorithm, I managed to show that by the end, the value of my final phi, which is going to upper bound the value of the maximum of ax, is going to be at most order root n. And that's it. Okay. Now, if you're interested, I can give you a brief idea for how to prove this thing. Like, the idea is that, basically what we're really trying to do is that we're trying to show that this matrix, that this matrix has a small eigenvalue in the subspace orthogonal to x. But of course, after I restrict myself to, just like the coordinates that I can still move, that I can still update. So let me just look at the matrix Qx, which is going to be the matrix A restricted to the columns S that are still unfrozen. Columns of A that are still unfrozen. And let me assume that at this point, the size of S is equal to K. So now my matrix is going to be something like A restricted to these columns. I just throw everything else away. Transpose. Okay. I can just like spectrally upper bound it times diagonal of some probable distribution P, which is exactly the probable distribution that shows up over here, times A. And what I want to prove is that Qx has a small eigenvalue in the subspace orthogonal to x. Now, okay, well, how do I prove the existence of a small eigenvalue for this matrix? Well, the simplest thing I can possibly do is to just bound the trace of Q of x, right? Well, because I know that the trace of Q is just the sum of its eigenvalues, and it has k eigenvalues. And the trace is basically just going to be the sum over all pi's times squared L2 norm of rows of the matrix. And okay, the crucial thing is that, once I use this magical regularizer, the square root regularizer, this is actually raised to the power 3/2. Okay. Now, the thing is that because my matrix contains entries that are bounded by 1 in infinity norm, and here I have only k columns available, I know that each of these terms is going to be upper bounded by k, right? It's just going to be a vector that's going to be bound, that has entries at most 1, which has dimension k. So, so basically this tells me that definitely the smallest eigenvalue, so I mean, okay, not only the smallest eigenvalue, but, half of the eigenvalues of this guy are going to be at most order trace over k. So basically it tells me that, so I know that my lambda min, for example, is going to be at most 1 over k times this whole thing times the sum of my pi's. Now, the thing is that typically I can't say anything interesting about this thing because, again, like if this probable distribution were spiky, this can be as bad as 1. But now let me just imagine this wishful thinking scenario where this thing is rather uniform. So let me just imagine that I'm in the case where, where all these PIs are maybe order 1 over k. In this case, I get something much better because I can make the sum, because once, what's the possible worst case for the sum is going to be when there are going to be exactly order k components in this vector that are going to be as large as possible. So this is going to make, the sum to be bounded by k times 1 over k to 3/2, which is basically, 1 over root k. So in that case, I would, in this wishful thinking scenario, I get something amazing. Now, of course, the problem is that it will not always be the case that my PI is going to be so uniform. But the thing is that, all I'm trying to achieve is to kind of prove that this matrix has a, has a pretty small eigenvalue. And the thing is that, this trace argument is kind of weak because, I'm just looking, I'm just looking at all the subspace and I'm just doing the dumbest possible averaging. What I can do is to basically just say, okay, well, let me try to ignore the subspace, that's spanned by the rows of this matrix that correspond to the largest k over 2 entries in this vector P. Well, once I do that, basically what I did was that I just threw away k over 2 directions in which I can possibly move. But then all the remaining p's are going to be bounded by order 1 over k. So that basically means that, this is going to enable me to certify that within that subspace, my trace is small, and therefore I have a small eigenvalue, which is going to be as small as I want it to be, order 1 over root k. So that's basically how you end up, how you get to prove this lemma. Okay. So basically, this pretty much wraps up the proof for Spencer. And we proved that we have this nice continuous dynamic that yields a good coloring, and if you just analyze everything very carefully, you improve on Spencer's constant. You prove that 3.67 standard deviations suffice. This is probably not tight. I think it's kind of conjecture that the right constant should be 2, but someone probably needs to work harder to prove that thing. But of course,
Adrian?
Yeah.
Could you just remind me the update delta? Are you adding it in with a random sign, or is the sign coming from the optimization?
Oh, the point is that you can always choose the sign to make this thing negative, right? The sign always comes from solving this optimization problem. Typically, if you did not have this constraint, you could always make this whole thing negative. Now, just because you have this annoying constraint that you actually want to make progress, you want to move orthogonal to your current x, well, it may just happen that this is gonna force you to make this term 0, and at that point, you just need to worry about your quadratic. But yeah, you're always free to choose the sign. Okay, thanks. Okay, so so basically, we can just test our tools to try to prove something harder, like maybe the Komlos conjecture. The problem is that for matrices, for matrices of this type, we can only certify weaker bounds on this second smallest eigenvalue of our matrix Q of x. The thing is that the key difficulty here is that in Spencer instances, the mass on the rows of A is very uniformly spread. So basically what happens is that, we have our matrix initially, each row has, entries that are at most 1 in absolute value. And then the thing is that I start freezing some of these elements. Now the thing is that the remaining mass keeps decreasing. So depending on how many variables I still have left available, that's going to give me a bound on the mass I still have available on the rows, on those rows. So this uniform spread is kind of essential to be able to prove things in this situation.
Could I ask something?
Yep.
So I thought, if I understood correctly, your algorithm for Spencer does not ever do a partial coloring. It kind of it gets a full coloring in one shot. Could you speak to that?
Yeah. Okay. So that's a very good point. So it doesn't worry about partial colorings, but the thing is that it still suffers from the curse of partial colorings in the sense that, basically whatever you pay for before you manage to freeze half of the coordinates is going to dominate whatever you end up paying in the future. Now, the problem is that once you look at problems like the Komlos problem, is that, okay, you pay something, you pay 1 until you freeze half of the variables, but then the speed of, the speed at which your fee increases is going to double. So the point is that, now these things increase twice the speed, and that's how I end up accumulating some extra log, which is going to be very annoying. So basically, to be able to get rid of this thing, you kind of need to somehow take advantage, you kind of need to leverage this sort of uniform spread property, which really does not come for free. Because the reason is that, basically you can just try to look at, the Spencer instance. So, you can just measure the speed initially. It's going to be bounded by, 1 over root 5, then 1 over root 4, 1 over root 3, and you get exactly what you need. If you want to replicate this sort of behavior for a Komlos instance, you really want to get some much tighter bounds, The thing is that such things are not possible because it may just happen that you might actually have a whole bunch of rows of your matrix that really contain a lot of mass. So that's not really gonna work. I mean, basically, if you wanted to be able to get the same type of bound over here, you really needed to, always be able to say that, at all point, at all times, all of my remaining rows have some, have like some very small amount of mass. That's not even true in the beginning. Now, the problem is that, okay, so, yep.
So this seems like the more interesting obstacle, but you also have an obstacle in the initialization, right?
What's the obstacle?
The constant root n that you get out of the
Sure, but you can vary your regularizer. So the things that, okay, so that's just an example that I use specifically for the n by n Spencer instance. Even when you have a different m times n, I use a different type of regularizer. It's not gonna be square root. It's gonna be it's gonna be x to some power. So that I need to choose carefully. And yeah, so I mean I agree with you. Like, the point is that, ideally I would have liked to be able to use the same type of regularizer, just like pay a root n up front, and then just multiply it, and then just take, just like, okay, I would have just wanted to pay a root n up front. So, okay, the things that, okay, you can always put like some weight on your regularizer. So maybe I can scale it down, and in exchange, I pay more for the speed. So in the end, you end up paying something like the geometric mean between how much your regularizer contributes at 0, and how much you pay for this, because of for this, for the speed of increase of your fee. Now the point is that if somehow I manage to control, like the spread of these rows, then I would have gotten exactly what I needed. And this is not generically true. But the thing is that this kind of condition does actually hold for random matrices. Like, basically, for random matrices, actually, like if I just generate, for example, I just like each of these elements is some IID Gaussian, for example, I get exactly what I need, more or less. And like, basically, Potokuchi introduced some pseudo-randomness condition that he used for for the Beck-Fiala problem. And basically, if we just like work our way around that sort of pseudo-randomness condition, we pretty much exactly get what we need. We get exactly the type, we get some sort of uniform spread, modulo some rows that are gonna cause us some trouble, but we can just ignore them temporarily and get back to them later. Now, formally, what does the pseudo-randomness condition? What is the pseudo-randomness condition that I'm talking about? It's basically looking at something like this. Imagine that A is my matrix, and I'm going to look at the maximum over all vectors orthogonal to the all ones vector of the L2 norm of my matrix pointwise squared times V divided by the L2 norm of V. So this thing is kind of, let's just like try to understand this thing, for example, in the case when A is a symmetric Komlos matrix, for example. Let's just imagine that, all the rows have L2 norm exactly 1, and let me also make it symmetric. In this case, this pointwise squared matrix is just going to be a random walk matrix, right? And I know just from Perron-Frobenius that, the all ones vector is just going to be the largest, the largest eigenvector. So basically what this thing is essentially measuring is going to be the spectral gap, right? When I have a large spectral gap, this lambda is actually going to be going to be small, right? So what we're proving here is that when we have a huge spectral gap, which corresponds to the case where this looks very random, we actually get something better than vanilla, than the current bounds that are known from Komlos, right? We get a discrepancy of like 1 plus square root lambda log n. So when lambda is like significantly smaller than 1, we actually manage to get an improvement. And for example, in the special case of random rotation matrices, this is actually very small. It's actually something like 1 over root 10. So in that case, you actually get discrepancy order 1. And there are a whole bunch of other examples where this thing works. Now, of course, it'd be kind of interesting to go beyond these random instances. So again, I'd be very curious to understand, just what happens for the case of rotations, but in the worst case. I was talking, just yesterday, I think that Hautian was mentioning that if you manage to prove anything like that for worst case rotations, that already implies some very interesting facts about lattices. So that's probably like the first problem you want to look at if you're trying to attack this conjecture. Now, I guess it's kind of time to wrap up. So basically, what we did was that we used some interesting regularization to solve problems in combinatorics, and we managed to simplify many results because I think that the algorithm is extremely small. It's extremely simple, right? Just execute a sequence of Newton's method, and you're done. So we managed to strengthen generalized Potokuchi's result, and we proved that Komlos actually holds for interesting random instances, which also happens to refute some paper that was the conjecture that was put forth in some paper that was kind of trying to argue that basically there was like some older paper that was kind of trying to argue things about the density of good colorings for Komlos instances, and basically that paper was roughly conjecturing that random rotations could actually be a hard example for Komlos, and it's actually not. And there's some interesting food for thought, which is just trying to prove something about worst case instances not random. And we have like these very structured worst case instances, just some fixed rotation, has a very nice geometric statement. Basically says that no matter how you rotate an n-dimensional hypercube, you're always going to have a vertex that's close to the origin in L infinity norm. So if you manage to prove that, that'd be huge progress. So yeah, that's about it for now.
Any questions for Adrian?
What is the ultimate runtime that you get?
Oh, good question.
Say for Banaszczyk.
Yeah. Okay, so this is not going to be a fast algorithm, right? So for example, if you execute this thing, I think you can do it in something like ON steps. And if you don't do anything too smart, I don't know, you probably get something like n2 omega plus 1. It's not great. I think that Yang and some other people already have something that runs in input sparsity time for Spencer and stuff like that. So there are definitely other works that achieve fast algorithms, but they use different methods. Thanks. So I'm more concerned with the existential aspects than the constructive ones as far as discrepancy goes.
You alluded to a connection to lattices at the very end.
Yep.
If you can you say something about the conjecture there?
Okay, I can't say anything. I can't say anything specific. I think that there are people here who are experts in lattices.
Okay.
I don't want to go there, but I think that if you stare hard at them, probably you're gonna. Lattices kind of pop up naturally. I don't maybe someone else can say something specific.
Yeah, this looks very connected to the lattice problems, but I was just wondering if there, some specific technical connection.
Yeah, I'm not sure. Okay.
Just a more general version of my question of runtime. I know that I think a balanced walk gives a linear time algorithm for Banaszczyk's theorem, but is it the only approach? Basically, what are the? It's not immediately related to your talk, but what are the currently known approaches for producing Banaszczyk style colorings in linear time in the
linear time.
current and in the input size?
Okay.
Is it just balanced walk, or is there more?
Get the right bounding. I don't know how to.
I don't care about polylogs, let's say.
With polylog, I think probably running something like that with Spencer, like.
Yeah.
So only
mean,
balanced walk and derived.
Oh, so you're saying
approaches.
that like if you want to get squared log, nothing fast is known, or?
Yeah, I think so. Square root log, nothing's known. Log, you can probably run like some algorithm for Spencer, and there's various.
Like a partial coloring is already gonna give you the log if you want to. So whatever works for Spencer is gonna work for Komlos more or less.
Thanks.
Could I ask for So on
Your previous slide, when you said you got the bound of 1 plus O of root lambda log n, is it true that lambda's? It seems like lambda is always on most 1, so it does generalize Banaszczyk's bound.
Okay, so you have to be careful. So I mean here, wait, sorry, can you say that again?
Is it true that lambda is always on most 1?
So, okay, if your matrix is symmetric, it is true, right? Just because per Frobenius, whatever. If it's not, I mean, it can actually be larger. But, like for interesting cases, whenever this is random, pseudo-random, it's going to be below 1.
Got it. So I guess I was just asking whether this theorem generalizes, like whether your techniques give an alternate proof of Banaszczyk's bound.
Oh,
I guess that's the direction
yeah,
I
I
was
think
coming
that you
from.
probably need to work a bit harder. I mean, like I think that this kind of this is like probably not exactly the right condition you want to use here. You probably want to relate this thing directly to the spectral gap of this matrix. Like this all one's vector is kind of a stupid choice. So we can probably work around it. I mean, my bet is that it's gonna work if you play with it for a bit.
Anyone else? Let's thank Adrian again. And now we have a 30-minute break until